Hello, welcome to the first video for section 4.2. So given a matrix, there are a couple of subspaces sort of naturally associated to it. So let's talk about the first one. The null space of an m by n matrix A is the set of all solutions to the homogeneous equation, our old friend. So the null space is all of the x and Rn with the property that if you hit them with the matrix A, they get taken to the zero vector. So this is going to live inside of the So the first theorem we come to is that the null space of a matrix, and by a matrix at least, is a subspace of Rn. And the idea is what? You should check. Check 0 is in the null space, and that makes sense because we know that if we take any matrix and hit it with the zero vector, we get back the zero vector. So that should check it. We should check, So that 0 is there. Also check if U and V are in the null space of A. And then so is the sum. And this should make sense because why? Because to check if something is in the null space, we hit it with the matrix U. And this should just be equal to A applied to U plus A applied to V. If both of these are 0, then so is that's also going to be 0. And similarly, for the scalar multiple, if A of U is 0, then A times C of U, we can just factor out the C and get back C times 0, so it should be 0 still. If U is in null A, then so is C of U for some scalar C. So maybe this is less of a proof idea than more of a proof. Just go do it yourself if you're curious. Okay, as always, concrete example will make this easier to understand. Okay, so we've got the null space of this matrix. So if we were looking at just as a tangent, if we were looking at a transformation that took x and mapped it to ax, then what? This would eat a 1, 2, 3, 4, 5, 6, so a vector in R6, and produce one in R4. So this is a transformation from R6 to R4. Okay, so our solution is going to be, we need to solve ax is equal to 0. So again, it sounds like maybe we're learning new things, but actually it's going to come down to solving a linear system once again. Okay, so let's just row reduce our matrix to get all the solutions we want. So A is equivalent to, what do we want to do here? Maybe the obvious thing. R2 minus 2 R1. We can do R3 plus R1. So our first row hasn't changed. Second row, 0, 1, negative 2, 5, 3, 6. Our third row, 0, 7, 5, negative 3, 2, 4. And our third row, our fourth row at least hasn't changed at all either. Okay, and this is a 6, not a squiggle. Boom. Yeah. Okay. And this whole thing is equivalent to what? Let's do R3 minus 7 R2. We can do row 4 minus 7 row 2. So our first row hasn't changed. Neither has our second. Here we got 19 minus 38 minus 19 minus 38. Move that 6 over. And 0 and 0. 16 minus 32 minus 16 minus 32. Boop. There we go. Okay, and yeah, let's scale the third and fourth row just to make them more manageable. Let's do 1/19 of row 3, 1/16 of row 4. Okay, and these first two rows haven't changed at all. 1, -2, 5, 0, 0, 1, -2, -1, -2, 0, 0, 1, -2, -1, -2. That's 6, keeps on creeping. All right. Okay, so then we can do row 3, or rather row 4 minus row 3. 6, 0, 0, 1, -2, -1, -2. That's 6 forever. Give me a hard time. Finally, row 0, yeah, row 4 is just all zeros now. Okay. Getting there. We are getting there. Okay, let's do, yeah, row 1 minus row 3. We can do row 2 plus 2 row 3 to get back what? 1, 0, 0, 0, 3, 2. 0, 1, 0, 1, 1, 2, 0, 0, 1, -2, -1, -2, and then a row of all zeros. Okay, and now we are in reduced echelon form. Okay. So what? Always a good question. So now we've got what? It looks like x1, x2, and x3 are all bound. x4, x5, and x6 are all free. So we're going to get x1 is equal to what? Minus 3x5 minus 2x6. x2 is minus x5. Sorry. Minus x4 minus x5 minus 2x6. And x3 is 2x4 plus x5 plus 2x6. And x4, x5, and x6 are free. Oops, not there yet. All right. Yeah. So then how does this give us a null space? Well, I'll show you right now. x1, x2, x3, x4, x5. So this is all things we've seen before. All we're going to do is rewrite this general vector to satisfy the these equations. So x1 is now negative 3x5 minus 2x6. x2 is negative x4 minus x5 minus 2x6. x3 is 2x4 plus x5 plus 2x6, and then x4, x5, x6. Okay, so we can rewrite this as, well, let's look at everything that has an x4 in it. There's nothing there, a -1, there's a 2 here, and then a 1, and then 0, 0. Everything with an x5 in it. -3, -1, 1, 0, 1, 0. And then an x6 is going to be what? -2, -2, 2, 0, 0, 1. Okay, so we're saying that the solutions to x equal to 0 are exactly things of this form. But this really is the span of these three vectors. So this is just the span of these vectors: 0, -1, 2, 1, 0, 0, -3, -1, 1, 0, 1, 0, and -2, -2, 2, 0, 0, 1. So this span is equal to the null space. Okay, so there's our first null space computation. There are a couple of notes that may not seem so important right now, but will be important later. The first is that anytime we use this procedure to determine the null space, the vectors that we produce are actually linearly independent. And the way we can see this is if we just ignore this top piece here, we get back 1, 0, 0, 0, 1, 0, 0, 0, 1. There's no way that we're going to get relations among this part of the vectors. So the whole thing has to be linearly independent. Right, and the second note is that we've got three free variables. And that yeah, it isn't a coincidence that's giving us 3 vectors in our spanning set. That'll be true in general. But the number of free variables is the number of vectors in the spanning set here. All right, that's everything I have for null space for now. I'll see you all in the next video talking about column space. Take care, everybody.